It is my pleasure to introduce to you Shakir Mohamed. I was going to say that all of you know him and he needs no introduction, but I will leave that for Isa this afternoon. He studied electrical and information engineering in South Africa, and then he studied his PhD with Subin Karamani in Cambridge and worked with Nando in the University of British Columbia. He's currently a staff research scientist at DeepMind in London, and he has done very influential work in genetic modeling. Thank you so much for coming.
Thank you. Thank you, everyone. It's my first time at DALI, and I'm really excited to be here. And it's really great to be welcomed by all of you into this very sort of intimate intellectual space. So over the years and over time, I've come to describe my own research and my own interest in machine learning as this search for the principles of reasoning and intelligence. And I think this is sort of a theme that maybe unites all of us in this room. And so, of course, if you know me a little bit, then you'll know these principles need to be or will be the probabilistic principles. And so over the years, I've tried to discover what those probabilistic principles of inference and reasoning are. And I'd like to today just take a short tour of the current way that I have been thinking about these principles of reasoning and what the questions are that we currently face. So I think it's good to maybe begin to go back to 1981, and Brad Efron gave his world lecture, and in that world lecture he described 4 statistical operations, and we will all know these 4 statistical operations. And the first operation always begins with what he called data enumeration, what we all know as the process of collecting our data, working with our domain experts, deciding what is the data that we actually have and the questions that we want to address. And this is obviously the basis of all machine learning, is how you actually collect those data. And based on that data, you can then do 2 things. One, which was what he called summarization. Summarization is the process of taking all the data that you have and pushing it together, looking at statistical trends, its properties, and what is the story that the data, when you look at it together, actually tells you. There is the opposite of this process of summarization, which was called comparison. Comparison is the process of taking the data apart, stretching it, look at what individual data point says, which is different from other kinds of data points. And so we have this sort of spread between summarization on one end and comparison on the other end. And then, of course, what unites this process of summarization and comparison is what we call the process of statistical inference, of how it is that you take the data that you have and connect it to the model that you have designed or that you have specified, or to that comparative process. And so the core question of all of us in this room is, what is it that happens in this box that we call statistical inference and operation? So, of course, in this bottom corner, when we think about data enumeration and we think about this process of summarization, we may call that the process of modeling. And in this other side, where we think about comparisons and data, then we will call that experimental design, how we actually do that interface. Where most of us in machine learning work is on this process of doing summarization and inference, how we do learning and estimation of model parameters. And then maybe the thing we don't do as much in machine learning, but obviously huge in other areas, is this area of comparison and inference, what we would call hypothesis testing. And I think these sort of 4 are always good to keep in mind in sort of how I ground my own thinking about what it is, those principles that we will do. And if you have your frequentist hat on, then obviously this distinction between estimation and testing will be very natural. If you are Bayesian, you may be tempted to reject this distinction between estimation and testing, because as a Bayesian, there's only the process of posterior estimation, and so those 2 things are the same. But whichever school that you apply and follow, we can learn a lot, and ultimately what we are interested in doing is finding the most refined, those ultimate true principles of inference, because in those principles of inference is where the principles of reasoning and intelligence lie. And so I think, this is sort of a philosophy of machine learning. I think it would be good to ground that sort of in some of the things we are doing today. And our ambitions have grown quite tremendously, as it should have. And some of us, and we've seen it in the workshops over the course of yesterday and tomorrow. So some of them are thinking about the triple aims of healthcare. Those of you who are working in healthcare will know this expression. This is the core problem facing all healthcare today: to have better clinical outcomes, to enhance the patient experience, to reduce cost. And clearly, one of the ways, and many of us who are working in healthcare say that we will achieve the triple aims of healthcare using machine learning, working with our domain clinical partners, and doing those kind of things. And tomorrow there's a fun workshop on that. Then yesterday we saw about this need to build these autonomous systems, increasingly autonomous systems that deal with the complexity, the uncertainty, and the variability of the world that we are in. And we also had yesterday, how is it that we scale our models up to do reasonable, larger scale, but are also fair and safe. And so these things together, when we actually present it, when we discuss that vision, this is when we talk about artificial general intelligence. We then sometimes use the line that AGI will be the last technology that we will develop, and that AGI is the thing that may help us address these principal problems. And it is then, if AGI is the solution to this, then the core question of AGI will be the question of inference, because it will be through inference that we will be able to address those questions. And then it will be, of course, solving AGI and making advances in those principles of inference are those advances in intelligence. So that's maybe the key point of this, is that those core questions of AGI will always be the core questions of probabilistic inference, and where we will have to put a lot of our effort and focus on. So with that in mind, I'm just going to discuss sort of some of the work we've done over the last few years, looking at these two different aspects. So the inferential questions, which are now those core questions which we are all trying to address, which will help us solve these intractable challenges of the world, means that we will need to have this kind of probabilistic dexterity. We will need to be able to look at probabilities, mold them like clay, manipulate them in different ways, so that we can actually solve problems scalably in different domains, apply to different data and in different ways. And if you enumerate, this is my current favorite list. Of course, the first inferential question that everyone will ask was to compute the evidence of data that you have seen. Because if you know the evidence, you almost know everything about your data, of course, conditioned on your model that you have there. Sometimes you don't want to know the evidence, but you just want to know certain moments of that data set, because summarizing the data is the first step towards analyzing data. And of course, what most of us think about in machine learning is this problem of parameter estimation. Whether we are doing it in the frequentist setting or the Bayesian setting, that's beside the point. And then we move on to actually using those models in the real world, making predictions of future data, unobserved cases based on ones we have seen, issues around planning that we discussed in the generative models and our workshop yesterday, of how you can look at expected costs over time given certain actions, sequence of actions, macro actions and options. And then moving on to this issue of comparison, how it is that you can then do hypothesis testing to compare two different scenarios or multiple different scenarios, and the other end of testing, which we also saw yesterday, around doing experimental design. How do you assess the information that you have gained from a base scenario using a new action or an intervention if in the causal setting, and then look at that information gain or expected information gain in certain. So these are some of the core inferential questions that I think in almost all of your papers, some integral of this form has appeared. And what's interesting when you look at all of these things, they all involve probabilities. And when we look at the problems that we have to model today, they are high dimensional. They all involve some sort of integral of some sort. Sometimes there's a derivative hidden in the integral, and we need to do a lot of manipulations to actually modify and actually do tractable problems with this. So one of the things that I have been, or that I always ask people to do, is maintain a structured approach to their thinking by thinking about the distinction between probabilistic models, the inferential principle that you use when you think about those models, and then when you combine an inference and a model to look at a resulting algorithm. And so the model that we have been looking at, because it is a generic test bed, are latent variable models. With a latent variable model, you can ask all these inferential questions. You can explore the different ways of manipulating manipulating these integrals, and you can make those advances in inference and AGI that we can use. So this is a good test bed, and I asked people to think about two different kinds of models. The one that we have used for many times in the past and through all the textbooks are what are called prescribed models using the language of Diggle and Grattan. And these models have a latent variable. You may have some conditional probability given by some function. It may be deterministic or stochastic itself. And then you have an observation model, a noise model, a likelihood function that you assign. And this is actually quite a powerful model, because choosing a likelihood function is actually making a lot of assumptions about the data. You say that you can actually know something about the probability conditional that the data has in the world. And that data and that knowledge that you inject is quite a bit. But simultaneously, as many of us were exploring this kind of prescribed latent variable model, other parts of statistical science, both in machine learning and others, in ecology, in phylogenetics, in finance, have been looking at what are called implicit probabilistic models. So these are models which are defined as simulators of data, right? You can create a simulator of your financial system. You can create a simulator of the phylogenetic tree and of the evolutionary system, and they may have a latent variable model, a source of noise, and then they just have this transformation function. It could be discrete, it could be continuous, but it will have some parameters, and that's it. It just simulates data. And we need to make this distinction between these two types of models, because the choice of the model influences what kind of inference we can use in that model, and then ultimately that will affect the kind of algorithm that we will develop and deploy and put into production and all these kinds of settings. So these are the two sort of things to do, and I'm going to start with a little bit of work on prescribed models and then focus a bit more on more recent thinking on implicit probabilistic model. So one of my favorite methods was variational inference, probably the one I've worked longest since I was a postdoc. So these are, if you are given a prescribed probabilistic model, a latent variable model where we have a likelihood function, what is it that we can do? And here the principle of learning, that inferential principle, is always driven by direct computation of this marginalized likelihood, what is called the model evidence. And I want to emphasize this word direct. We directly target this model evidence, and based on that model evidence, if we improve the model evidence, then we improve our learning, and this is the principle of learning. And the variational method and the variational principle in general just says if you have some complicated probability distribution, we can approximate it by some general class of approximating families, and we will try and minimize that distance. And there are many different kinds of inferential variational methods. All of reinforcement learning can be seen as some kind of variational method. All of information theory, lots of statistical physics are variational methods. But we're going to just we try to look at one particular variational method, and that was called this evidence lower bound, or the Jensen bound-based variational method. And this was sort of the most natural way, because it was the simplest loss function that had everything that you wanted from an inferential principle. It took the model that you did, gave you a tractable way of computing difficult and unknown quantities, these posterior distributions Q. It allowed you to model the data fidelity using the likelihood function that you chose for your model, and it naturally included these kind of penalty functions, those kind of regularized it. It was not up to you as the human to think for days and years about what the right kind of regularizer for the data was. Just by the choice of the inferential principle in that model, these things came up. And so this was one of the natural questions. And so a lot of the work that we did was then to ask, how is it that we can turn variational inference into a generic tool for inference that we can deploy in many different problems across many different domains, and at large scale and at small scale? And I think this kind of question is still ongoing and still a core, very interesting question to ask these days. So the first thing that we thought about was this idea of amortized inference. So let's just write this free energy at the top. And the classical method that we all taught in machine learning was to do the EM algorithm. The EM algorithm is very simple. It says do an alternating optimization between model parameters and parameters of the thing that you're doing inference, right? So in the latent variable model that I showed above, we have variational parameters phi, and that is the role of the E step, because E is about expectations, it is about inference, so we will solve those inference problems, and then once you have solved this E step, you can then do the M step. This was the most incredible algorithm to have ever learned, because it told you this was a bound. Every step you did needs to be improved. You would do monotonic improvement, you would have convergence guarantees, all the knowledge you had from optimization would come in. And so this is the picture to keep in mind, that you would take into a box the model that you did, this kind of approximating family-based and variational inference. You would squish them together in this box, and the traditional EM style would say, first solve this integral, and then based on the integral, compute derivatives. And we spent years doing sort of lots of local variational methods, papers doing sort of piecewise approximations to try and compute these gradients and compute the integral in closed form. But that was something that required a lot of manual work, was not general purpose, and did not really scale to very large settings. So we had to find something different. So sticking on the amortized inference, if I unpack what the EM algorithm looked like, the EM algorithm, if you remember coding it, always looked like this. You always did def E step, and then you created a for loop for I equals 1 to n of the whole data set. It doesn't matter, you could do this in a stochastic approximation by subsampling the n as well and taking averages over the gradient. But you would always compute this key line, which means you would solve the variational parameters for every new data point. For every new data point, you would redo the optimization. You would get a set of parameters just for that data point, and then you would move on. And so the limitation of this point is that when you did an inference for data point n, you would not use that knowledge to help you improve your inference for data point n plus 1. So this was the limitation that we saw in variational inference, and where this issue of wanting to do amortization comes in. You wanted to spread the knowledge of the inference you had over all the data points to help all other data points. And so this is what amortization means, so that we would then fix those things. So then the idea of this amortized inference was then to introduce these new models, a new model which would, instead of having per data point variational parameters, would introduce a set of global parameters. And these global parameters would be shared across all the data points. And what happened here? Sorry. Updates on a Mac. Is it back? Okay. You would get these global parameters, and those global parameters would help you share statistical strength over all the data points. You would be able to do faster inference. You would do faster efficiency. And so this is where what we called a recognition model or an inference network. And so, as I said, instead of having these local parameters, you now introduce a new set of global parameters. And these global parameters are applicable to both training time and test time. Remember, in the classical EM algorithm, you would even have to resolve the E-step parameters at testing time, which then made it very slow. So that's, as I said, you amortize the spread of cost over the inference of data. And what you can now do is, because you have two sets of global parameters, you have global parameters of your model, but you also have a global set of parameters for your inference network, you can now do joint optimization. You don't need to do this alternating optimization anymore. So when you see an inference network or an encoder, because people very generically throw encoders at everything these days. When you see an encoder, you should ask the question of what is the thing that is being amortized underneath it? What was the underlying alternating optimization that is being removed? And you will see this in optimal transport. People will put an encoder, but the optimal transport will say, well, there's an infimum, you solve it for every data point. And so amortized inference is a way of doing posterior inference with memory. And when you see these encoders, you can think about different algorithms to solve it and what's actually being addressed. So there are several important questions around amortized inference which still need to be addressed today. One of them is, how do you actually understand the principle of correctness when we introduce this new global set of parameters? And you can do a very fluffy proof to say that if you have a generically powerful Q distribution, then you'll be able to reach the optimal solution that's given by the functional derivative. But doing a deeper analysis and doing a deeper proof to show exactly what is correct is still unknown. So this use of inference networks can be a bit fishy. And then we've also given up certain things. By leaving behind the EM algorithm, we cannot deal with missing data anymore the way we used to do. Missing data was never a problem in the classical probabilistic setting. Any missing data just gets ignored, you don't include in the likelihood, and you just proceed. But now, if you have missing data, you would have to train an inference network for that particular set of missing data. And so now we seem somehow less flexible than we used to be, even though we can do more training. So this is one idea of amortized inference. The second question that we needed to do was, how do you build those posterior distributions that help you reach the true posterior distribution? We can't just be building products of Gaussians anymore. That day has ended, and no one should be doing that anymore. So, of course, when you deal with this kind of posterior approximation, you have this spectrum. You have on one end the true posterior distribution, but if you knew the true posterior, you wouldn't be doing any of this. And then the other end, you have this least interesting probabilistic estimate. You have this fully factorized distribution. And there's now a spectrum in between, and over several years of work of many people in this room, we have looked at different families of posterior approximation, different kinds of covariance models. How is it that you can build a Gaussian with a richer covariance model that still helps you do efficient inference? Roger spoke about an interesting way of doing that yesterday at the generative workshop. Then structured mean field, many of us have thought about how we can introduce additional structure using autoregressive models and other kind of structured methods. We can do mixtures, we can do copular methods, we have auxiliary variable methods where we can integrate our certain things that help us maintain the distribution. And the one that we spent a lot of time thinking and still think is a good generic tool is what we call normalizing flows, which is what helps use the change of variables rule. And so I think, so here there's still a lot of different questions. What are these general purpose posterior approximations? And what is interesting in this regime is that all the problems of probabilistic modeling are what you use to design these posterior approximations. So if you knew how to derive a good model, you could also use that to say how to do a good posterior. Many of these methods will still not scale in very high dimensions if the latent variables are very high. And if you have hierarchical models, then this is one of the research questions. How do you do inference in hierarchical models? The last idea which came up was how we do stochastic approximation. So in that previous picture of the EM algorithm, these two blocks were swapped, and the simple idea that we all had at this point was around 2013, 2014, was just to swap these two blocks around. And then it was the question of how do you actually swap these two blocks around? And when you wrote the integral, this is sort of where the insight, let's just write the integral. You said compute the gradient of the variational parameters phi, which is an expectation of that variational distribution under some function f. It turns out this is one of the most generic problems in all of statistical science. It is the same problem which appears in operations research under queuing theory. It is the same problem which appeared in stochastic optimization. It was the same problem which an entire textbook has been written about computing this gradient in finance. And of course, it was the same question of variational inference and of even reinforcement learning. So it turns out there are four generic ways or four generic principles for computing this kind of gradient. The first one is called the weak derivative method. The second one are the harmonic gradient estimators, but these two are not useful for machine learning because we will not be able to scale them up. So instead we use the remaining two, and there are two things you can do to this integral. You're either going to manipulate Q, which is the density, and if you choose to manipulate Q, the estimator of this gradient you will derive will be called the score function estimator, also called the likelihood ratio estimator. In reinforcement learning, they will call this the reinforce estimator, and in stochastic approximation, there are many other families of these kind of estimators, which just says compute the gradient of the log of this, and you upweight based on the function. And you would use this when you can't differentiate this function or you can only evaluate it. Very useful for reinforcement learning. The other thing you can do is, of course, manipulate the function itself. And so if you can manipulate the function and you have a way of rechanging the distribution that you're taking the expectation with in terms of a variable transformation, then you can use this estimator, which is called the pathwise estimator. It's called the pathwise estimator because you are using this path of simulating this random variable. It has several other names. Of course, we called it stochastic backpropagation by using this thing in our own work. Other people these days call it the reparameterization trick. If you are reading in Monte Carlo, then you will call this sort of the non-centered parameterization. And in stochastic optimization, you have various other versions of pathwise estimators. And we can do a lot of work on these two things. And so the questions around stochastic optimization still exist. Can we do greater scaling? What kind of new estimators exist? Can we use these tools into generic probabilistic programming tools? And I think a lot of work is happening in that regime. And even though the variance properties seem to be something we don't talk about and are easy to compute in simple cases, really what are the variance properties when you do such estimators? So that leaves behind sort of these prescribed probabilistic models. And much of the work we've done over the last 2 years maybe is around inference in implicit generative models. And inference in implicit generative models is you can call by several other names, and the one of the names that I like is called inference by comparison. Comparison was this other side of Efron's for statistical operations. And so in many models, you will not have access to the likelihood. You will only know this in some unnormalized way. You will only have partial knowledge of the distribution. And so what do you do in these kind of settings? And so the simple setting is that you will use the most classic method of computing distributions. You will compare two distributions. You will have your true data distribution where the data comes from P star, and you have your model Q, and you will try and compute and compare them in some way. And so you can derive a lot of different ways of estimation by comparison in this way. And so the principle of inference here is based on two-sample testing. You can do Bayesian versions of two-sample testing or other ways, and there are typically only two ways you can do it. You're either going to compute the ratio, and when P divided by Q is 1, then you have done learning, or you say when P is equal to Q or P minus Q is equal to 0, then you have solved it. These are the two classical ways of doing hypothesis testing as well. The world estimators, Bayes factors all look like this. So this is the thing we want to compute, and the key point of this is that unlike the direct estimation that I said before, where you would directly target the marginalized probability P star, here you're not interested in that. You're only interested in knowing it relative to something else. And knowing the marginalized probability relative to something else is actually a far easier problem than knowing the marginalized probability. And so that's the idea that we're going to try and exploit. So density estimation comparison, you can do it in several different ways. You're going to have maybe your the standard hypothesis that P is equal to Q, and you're going to have the alternative that it's not Q, and you're going to try and make that decision, and you're going to introduce a loss to help you learn that. And any density estimation by comparison, like the EM algorithm, is going to have these two steps. The first one is a comparison step. You're going to use some kind of statistical test or a comparison, however you define that, to tell you whether the data you simulated from your model is similar to the data that you actually observed. And you can do this in many different ways, and it will be interesting to discuss what people think are good comparison methods. And as I said, you can do this by computing the density ratio. You can compute P divided by Q, or you can use it by computing the density difference, P minus Q, and then some modifications of the integrals around this. And so if you want to do the density ratio method, Masashi is not here this year, but I think he wrote the entire book on computing density ratios, and you can do this in at least three ways. The main way is to do class probability estimation, but you can use this through F divergences. Sebastian can tell us a lot more, and through Bregman divergences that we also have. And all of them can be sort of interchanged and swapped, and there's an equivalence between them. And if you wanted to do the density difference, then moment matching is one of the classical methods. I'll try and describe that a bit later. Arthur is also in the room, and so he can tell us a lot more about maximum mean discrepancy and the kind of methods that come from maximum mean discrepancy. And so all of these give you a way of doing testing and comparison, and once you have that comparison, you can then use that to do estimation. You can then adjust the parameters of your model to make sure in the direction that the comparison becomes equal or reduces. So these are the general principles, and you're going to see a lot of methods, and you can even think of other methods that you know. So here's the first way, which is to do density ratio estimation. So the problem is we have an implicit probabilistic model. I just want to check the time. We have this implicit probabilistic model. We can sample from it, and we have a generative model, and we're going to do some comparison. Now, the classic trick of density ratio estimation says that any density ratio estimation can be computed by the ratio of a class probability. So you can build a classifier that classifies from P star to Q, and if you know the probability, then that ratio, you can compute this in this other way. So obviously, you can derive a classifier, which means you must assign a scoring function. Based on the scoring function, you can then assign a proper scoring rule, and any scoring rule will be valid. The one here is the log loss. And then you will do this alternating optimization between the functions of the scoring function, which are theta, and then the parameters of the model, which live in Q, which are phi. And you will just alternate these two things. So many instances of this throughout the literature. If you check in the book on elements of statistical learning, they will call this unsupervised as supervised learning. It's obvious, right? Because you want to do unsupervised learning of this model, but now you build a classifier so it becomes supervised. In ABC, they are now doing exactly the same thing, approximate Bayesian computation, where you build a classifier to help you decide the moments. Noise contrastive estimation uses the same principle, but with a little bit more knowledge, you can change it. And then GANs, which are very popular these days, are also based on this very same principle. So if we apply that principle in the GAN setting, the comparison step is to then use exactly this loss function, and then to compute gradients with respect to theta, which are called these are the discriminator parameters, which is doing this comparison step. And then the estimation step is just to take a gradient with respect to the model parameters. And a lot of thinking goes into what are good losses for estimation and comparison. And because of the way the setup is here, the loss you use for estimation does not need to be the loss for comparison. And I think just the key point to go here, which is different from variational inference, is that density ratio estimation and this kind of estimation comparison says that you can do inference or parameter learning without needing to do posterior inference. And I think that was a really magical, it's kind of mysterious that you can actually do that. You did not need to compute the posterior to learn the model parameters, which was what variational inference said was not possible to do. So I think that's interesting. So more recently, we've gone back to a more classical method. The first method of inference presented to us by Pearson himself was the method of moments. And the method of moments is almost too generic a principle of inference, but I think is good because it avoids the deficiencies that we're seeing in other cases. We have very poor theory. The theory is not translating into practice. We have instabilities in optimization. And many of these things can be resolved by going back to this more classical method. So the method of moments simply says design a moment estimator. And of course, we all know this because when you choose this function f integrated against p as the gradient of a likelihood function, this is when the method of moments becomes what we call maximum likelihood. But you can change this f to be any kind of function. And so, of course, we just saw in the previous slide when we did density ratio estimation that a good function is to use a classifier. But we also want to use a little bit of maximum likelihood, which is said the features, which are called f here, are gradients. So we actually went to go and look in the kernel literature instead. And in the kernel literature, they were doing a lot of work around linear SVMs and thinking about how you can build auxiliary models to give you features. And there was a really interesting paper, which they called the tangent of posterior odds, which is how they would derive their feature. And so here's the posterior odds, which is the same as that density ratio. And you can compute the gradient of this log. And the gradient of this log are features that you can then use to do this comparison step. And gradients are one of the most powerful things you can use for comparison. And so that's what happens. And then you can specify a moment loss or moment estimator. And here you would specify any sort of minimum distance estimator. A minimum distance estimator would then have all the asymptotic properties that you want. Asymptotic normality, asymptotic convergence. You would then be able to prove the rates of convergence. You would know its bounds. You would know the asymptotic variance. And then you would modify this loss based on the asymptotic variance as well. So I think method of moments is one of the most really good things to re-estimate. And Pascal sort of reminded me to go and read a little bit more about this yesterday. So it looks very much the same as before. You would have your implicit probabilistic model, and then you have a moment network, and you need to define what these functions are, and you would have these losses. And how we define our moment network is a function, which is a classifier, and the moments are now all the gradients of that method, all the features or activations of that network itself, and then a bit of the data also. And so then you build this big vector, and these are the two things that you are matching. And so the power of method of moments is that you get these consistent estimators, and the theory, the asymptotic theory even tells you that you just need to ensure that the number of parameters of your features is greater than the number of parameters in your model, and if you can satisfy that condition, usually it's 2 or 5 times more, then you will be able to have a consistent estimator that will have all the properties that you need. It will tell you exactly what kind of features they need to be, so you need to have features that are not collinear, hence the need to use gradients and why gradients are useful. You can create a system now that will be far more stable than the kind of adversarial training that we have before, and you don't need to do testing stage, do estimation stage, and you don't need to do 1-1-1 updates. You can do one moment update, 5,000 updates of your model, and then go back. And so lots of questions still about here. What are the right types of feature functions? What other kinds of methods do we get? And what is the deeper connection between all the sort of hype around adversarial training and statistical efficiency, and clearly there is something deeper coming up. So, and then the last slide is just that there are many more convergent approaches coming up. When we look at variational inference, and now given these two kinds of tools that we have, you can see that the KL divergence is itself a density ratio. So wherever you see density ratios in variational inference, should you be replacing them by classifiers in other ways? We've also been rewriting this free energy lower bound in different ways to expose other properties. So we write it in this way by expanding this KL to say that it's a KL between marginal distributions and some information term. And then you can see lots of different, so should we replace this by a density ratio or classifier? Should we replace this by a classifier? And there are lots of questions and many different approaches and many people in this room have worked on that kind of interface. And you can even see optimal transport as deriving this bottom bound and connections to integral probability metrics that we've been thinking about as well. So lots of different models in this setting appearing, and none of them are quite working yet. So I think there's still a question there. So how do you scale to higher dimensions? How can you do meaningful evaluation in these models? What are better sampling methods? And how can you improve those models? So this is where I wanted to end. I sort of wanted to begin by just grounding things in Efron's 4 statistical operations. And those 4 statistical operations remind us of the things that we are sometimes forgetting to look at when we are dealing with our research. And we looked at 2 different types of latent variable models, prescribed probabilistic models and implicit probabilistic models. Those 2 choices of models mean that you will have very different types of inference you will have to do. In prescribed models, you can do variational inference, but in implicit models, you will have to do some kind of inference by comparison. And so we looked at amortized inference, generative adversarial networks, the method of moments, and I think there's a lot more to do. So my search for those principles of reasoning and intelligence are still going on, and I look forward to seeing what together maybe as a collective we will do in addressing that question over several years. Thank you. Too early.
Too clear to...
One question. So, if you look at probabilistic modeling, right, a few years back, this is blossoming of Bayesian non-parametrics, where we have models which have, acid and they create entities where needed and so on. And it seems it was curiously absent in some of these variational methods that I use in the learning community, right? What's your thought on rich latent representations that have, say, entities that could create a brought to existence, reason on a lot of existence, that could scale more to like real-world settings? Because we seem to use always like 100-dimensional or maybe 1,000-dimensional vector, and that's
actually, it's interesting. When the wave of Bayesian non-parametrics ended, a very different wave began, taken by deep learning, and these days it's not called that. So you'll find a lot of methods which are based on external memories, right? You will find people who are building these differentiable stacks, right, or differentiable queues, or they will be embedding nearest neighbor methods into the model. So the model will actually have this table which can grow over time, and they will just store activations of LSTM or of the latent variables of a model. And this is a different instantiation of this non-parametric question. And that, I think, has been very successful. You can scale that up. It actually does work. It has all the properties that you just mentioned of growing over time, having new instantiations, being able to be summarized. So I think it would be useful to re-examine this new approaches with the lens of non-parametrics. But the reason that non-parametrics, we weren't able to push that further was because this problem of inference in non-parametric models was very hard. So, if we could solve the problem of inference in non-parametric models, we wouldn't do any of this other stuff, right? We would have solved the problem already. You could just build a DP on everything, a DP mixture of everything. So I think that's why, even more centrally, the problem of inference becomes more important, because these kind of models that we know about non-parametrics we aren't able to use, because this is what's holding us back. We can't be implementing Radford-Neal's algorithm number 7. It's not going to work in 2018. So, yeah. Okay, thank you. Oh, yes, Sami.
What do you think about the parameters of the model being random variables? So most of what you talked about today is primarily about the latent space. So the encoding space. Do you have thoughts on the interaction?
So I think that's also, that's maybe the most important question to address in inference right now. And the reason, so maybe this goes to Sebastian's point. If we could be more non-parametric, then that problem would disappear, but then we have other kind of problems, and we aren't actually able to scale up. So when you have 1 million parameters, 10 million parameters, 100 million parameters, then the simplest thing to do is just to build these kind of fully factorized distributions as posteriors, and that doesn't work. So then you could try to do these kind of density ratio methods, but they do not scale to more than 1,000 dimensions. Actually, you can do a lot of experiments to look at to what extent do they give you useful learning signals, and when the dimension gets high, they stop working. So I think that question is one that, I don't know, I'm trying to think about, but don't have a good answer for. Simon.
So what about decision theory and the interaction with inference?
Okay, so we need to do one more. Now you need to read Jane's book, because Jane said very clearly, right? He said inference is the question of what you can know from your data, and decision theory is the thing of what you can do with your data, right? And so all of this is missing that last step. Now that you've solved the problem of inference, what do you do? So reinforcement learning will add that one step of decision theory. Experimental design will add one more step. The loss-calibrated Bayesian will add that one more step. So I think, it's not that we aren't thinking about it, but there is a sequence of things that need to happen. And then you can think of different losses and what the losses mean for the task that you're addressing and how you can deal with that. So I think decision theory has a lot to teach us about how we can change our inference and our models as well. Yes?
So the way you talked about this landscape of inference is basically we have all the pieces, we just have to stick them together. And the question is that really explaining intelligence? Because in one sense, you talk about how to model your data, but life is more in the posterior world to pick the right models which serve a purpose. And to validate them in time so that you are not fooled by the wrong inference.
Yes. Okay, I don't want to get into the definition of intelligence, but let's choose a working definition that, just for the purpose of the discussion, is that what we would want to do is create an agent-based system that can do many different tasks with the same model, with the same agent, right? So now that is a very different problem of thinking in the abstract of an intelligent agent doing random things. This is a very concrete model. It has a very concrete set of experiences that it's streaming over time, and that decisions and actions and policies need to be learned. So when you do in that setting, then you will have to address the question of how is it that an agent is receiving a stream of information, learning online. So I didn't talk about online learning. Of course, that needs to happen. How it is building those models which are rich and adaptive and flexible over time, and there may be many different models. There's not going to be one model only, so maybe there are mixtures of those models. And in that setting, then the core question is, how do you do inference in those models? We are doing some form of inference. Maybe we don't, maybe we aren't. But if we're building a machine learning system, then there's going to be some form of inference. How is it that the data that is being observed, perceived, and streamed in needs to be combined with whatever model that agent is building? And that problem of combining data in a model is inference. And so that is why I'm pushing that argument that inference is this core to whatever reasoning or whatever we want to call intelligence. Because ultimately there will be data and there will be a model, and they will need to be fused. So, but maybe have a different thought, so you can retort. No one else?
Stand the speaker again.
Thank you.